For centuries, Mars has been a beacon in our night sky, a symbol of the unknown. We've painted it in our stories as a world of canals, of ancient civilizations, and of conflict. But as our telescopes grew stronger and our probes drew closer, a different picture emerged, a silent, frozen desert, seemingly devoid of life. Think Mars is a dead desert? A world of just rock and rust-colored dust, forever locked in an icy slumber? Think again, because beneath that serene, desolate surface, a story is unfolding. A scientific drama filled with tantalizing clues, frustrating mysteries, and the persistent, audacious hope that we are not alone. The closer we look, the more the red planet surprises us. It's getting interesting. To understand the Mars of today, we must look back billions of years. The evidence is overwhelming. Mars was once a water world. Our orbiters have mapped the entire planet, revealing features that are unmistakable. We see vast, dried riverbeds, some stretching for hundreds of kilometers, carved by colossal floods. We see intricate deltas, like the one in Jezero Crater, where a river once poured into a vast lake, depositing layers of sediment, a perfect place to preserve signs of ancient life. These aren't just superficial scratches. They are geological scars that tell a clear story of a warmer, wetter past. But where did all that water go? Much of it was lost to space as Mars lost its protective magnetic field and atmosphere. But a significant amount is still there, locked away. We found it as underground ice. Landers like the Phoenix mission literally scraped the surface and found bright white water ice just centimeters down. Orbiters using ground-penetrating radar have mapped enormous glaciers of frozen water, buried beneath layers of dust, some as large as the state of New Mexico. And what about liquid water now? This is where the story gets complicated. For years, orbiters spotted dark streaks appearing on crater walls during the Martian summer. These recurring slope lineae seem to be seasonal water flows. However, more recent analysis suggests they might be caused by flows of dry sand and dust, not briny water. The debate continues, a perfect example of the scientific process in action. The evidence for a wet past is certain. The evidence for liquid water today remains elusive, but the search is far from over. Water is the first ingredient for life as we know it. The next is chemistry. To find life, we need to find its building blocks, organic molecules. These are complex molecules containing carbon, often bonded with hydrogen. On Earth, they are the foundation of all living things. And on Mars, we've found them. The Curiosity and Perseverance rovers, our mobile laboratories on the Martian surface, have detected definitive signs of organic compounds. They drilled into ancient mudstones in Gale Crater, rocks formed at the bottom of a long-vanished lake, and heated the samples in their onboard ovens. The result? A whole suite of organic molecules, preserved for billions of years. Then there's the methane. On Earth, over 90% of atmospheric methane is produced by living organisms. On Mars, the Curiosity rover has detected mysterious methane spikes. The gas appears, lingers for a short time, and then vanishes. Its concentration ebbs and flows with the seasons, in a pattern that scientists are struggling to explain. Now this is where we must be cautious. These discoveries are not proof of life. They are possible signs of chemistry that could support life. Organic molecules can be created by non-biological processes, like interactions between water and rock, or delivered to Mars by meteorites. And the methane? It could be a sign of modern microbial life, burping out gas from beneath the surface. Maybe life. Or it could be the result of simple geology. Geochemical reactions between water and minerals like olivine, releasing the gas. Maybe geology. The data is tantalizing, but it's not definitive. We have found a habitable environment. We have found the chemical building blocks, but we have no confirmed microbes yet. To solve this puzzle, we need more powerful tools. Enter the robots. Our exploration of Mars is a triumph of engineering. Rovers like Curiosity and Perseverance are not just remote-controlled cars. They are billion-dollar nuclear-powered geologists. Curiosity's key instrument is SAM, or the Sample Analysis at Mars. It's a suite of 3 instruments that act as a portable chemistry lab, sniffing the atmosphere for methane and baking rock samples to analyze their composition. Perseverance, which landed in Jezero Crater, is equipped with an even more advanced toolkit designed specifically to search for biosignatures, the telltale signs of past life. Its Sherlock instrument uses an ultraviolet laser to spot organic molecules and minerals, while Pixel, a microfocus X-ray, maps the fine-scale elemental chemistry of rocks. Together, they can create detailed maps of a rock's texture and chemical makeup, looking for patterns that might have been left by ancient microbial colonies. These rovers are our eyes, hands, and laboratories on another world. But even these incredible machines have their limits. The ultimate confirmation of life on Mars won't come from Mars itself. It will come from here, on Earth. That's the goal of one of the most ambitious missions ever conceived: Mars Sample Return. Perseverance isn't just analyzing rocks, it's collecting them. It is drilling core samples of the most promising rocks and sealing them in ultra-clean titanium tubes. It then deposits these tubes at a designated cache on the surface, creating the first sample depot on another planet. The plan is to send a new lander to retrieve these tubes. A small fetch rover will gather them, place them into a container, and load them onto a small rocket called the Mars Ascent Vehicle. This rocket will launch into orbit around Mars, the first ever rocket launch from another planet. In orbit, another spacecraft will capture the sample container, seal it, and begin the long journey home. If successful, these precious samples could be in labs on Earth by the mid-2030s, where they can be studied with the full power of our best instruments, tools far too large and complex to ever send to Mars. And what about the ultimate explorers? Humans. While robots are our vanguard, the long-term vision for many space agencies, including NASA, involves planned crewed flights to Mars. Sending humans is exponentially more difficult than sending robots. We need to solve immense challenges, protecting astronauts from years of exposure to cosmic radiation, developing life support systems that can operate flawlessly for a 1,000-day mission, and learning to live off the land. This concept, called In Situ Resource Utilization, or ISRU, is critical. The Perseverance rover has already taken the first step with its MOXIE experiment, successfully producing oxygen from the thin Martian atmosphere. Future missions will need to extract water from ice and even manufacture rocket fuel for the return journey. A human mission to Mars isn't a race. It's a marathon of technological development. We're likely looking at the 2040s at the very earliest before we see human footprints in the red dust. This long, methodical search for truth often gets overshadowed by the hype. The moment we talk about Mars, imaginations run wild. We hear about terraforming, engineering the entire planet to make it Earth-like. While a fascinating thought experiment, the reality is we lack both the technology and the resources. A recent NASA study concluded that there isn't enough accessible carbon dioxide on Mars to build up the atmosphere needed to warm the planet, even if we could release all of it. And of course, there are the little green men. The search for life on Mars is not a search for complex organisms or ancient civilizations. It's a search for microbes, for single-celled life that may have existed billions of years ago, or might still be clinging to existence deep underground. The reality of space exploration is that it's slow. Each mission takes years to plan, build, and fly. Each discovery is built on decades of previous work. It's expensive. The Perseverance rover alone cost over $2.7 billion. The full sample return campaign will cost many billions more. These are massive national and international investments. And it's messy. Science is not a straight line to the truth. It's a process of debate, of testing hypotheses, and often of being wrong. The story of water on Mars is a perfect example. What we think we know today may be revised by new data tomorrow. So, what should we be watching for? The next decade is critical. Perseverance will continue to drill and cache samples in Jezero Crater. The Mars Sample Return Mission, a joint effort between NASA and the European Space Agency, will move from the drawing board to construction. Those missions mean answers within decades, not centuries. We'll also see new orbiters and potentially new landers from other nations, adding to our global understanding of the planet. The bottom line is this: Mars is more than a red dot in the sky, and it's more than a dead desert. It is a complex world with a dynamic past, a place that holds clues not just to its own history, but to the formation of our solar system and the very origins of life itself. We haven't found life yet, but we have found the best place to look for it. We are reading the pages of a book that's billions of years old, and for the first time, we have the tools to decipher its language. The search continues, one rock, one sample, one discovery at a time. The answer is out there, waiting to be found. Stay curious.